In analyzing the response and behavior of dynamic systems, certainly one cannot do a performance test that will cover all admissible inputs exhaustively. Therefore, the performance of controlled systems can be tested and compared by their responses to certain typical test signals. Among these test signals, we can mention, for example, step functions, impulse functions, ramp functions, sinusoidal functions, and others. In fact, the response that a dynamic system gives to a certain input signal can be analyzed in two parts. The first one is the steady-state response. It is the behavior of the output as time tends to infinity, that is, it's what you get after you wait sufficiently long. The other one is the transient response. It is defined as the behavior of the output as it goes from an initial state to a final state. That is, it is what you get until you reach steady state. There might be cases where you can't reach a steady state. For example, the output of the system may grow unboundedly. In other words, the system may be unstable. In fact, one of the most important characteristics of a dynamical system is stability. A linear time-invariant system can be stable, critically stable, or unstable. We are going to investigate these concepts in the forthcoming lectures in more detail. Let us start our analysis with a relatively simpler case, that is, first-order systems. Here is a unity feedback system where the feed-forward path contains only an integrator. Using simple block diagram reduction, you can represent this feedback system by such a single block. We are going to obtain the unit step response for this system, that is, the output corresponding to a unit step input. In other words, when R of S is equal to 1 over S. Of course, the Laplace transform of the output can be obtained by multiplying the closed-loop transfer function with the input. And to obtain the time domain expression, we can apply a partial fraction expansion and then apply inverse Laplace transformation. In this figure, we can compare the reference input to the output, and we observe that the output is a rising exponential. There are several interesting things we can note on this figure. Firstly, the output reaches about 63% of its final value in capital T seconds. Also, its initial derivative is equal to 1 over capital T. Finally, after 4 capital T seconds, the difference between the reference input and the output becomes less than 2%. All these observations shows us that the parameter capital T determines the shape and rate of the response. That's why it is called the time constant of the system. Let us also obtain the response to the unit ramp input. In this case, R of S is going to be equal to 1 over S squared. Again, multiplying the closed-loop transfer function with the Laplace transform of the input and applying a partial fraction expansion and then taking inverse Laplace transform, we can obtain the time domain expression for the output. Here are the time evolution of the reference input and the output. Again, the time constant capital T is in charge of shaping the response. We see that after 4 time constants, the output can follow the reference input with a fixed error. In fact, this final value of the error can be obtained by subtracting the output from the reference input and taking the limit as t goes to infinity, and that will yield the error as capital T. Lastly, we will find the unit impulse response of this first order system. So the Laplace transform of the input is 1 in this case. Therefore, the Laplace transform of the output will be equal to the closed loop transfer function, that is 1 over Ts plus 1. Or we can also write it with a monic denominator polynomial as 1 over T over S plus 1 over T. Once more, the expression for the output in time domain can be obtained by inverse Laplace transformation. So if the input is a unit impulse, the output is a decaying exponential with the initial value 1 over capital T. All these input-output relationships brings us in fact to an important property of LTI systems. In order to figure out this property, let us now collect the inputs and the corresponding outputs we have derived for them in a table. Up to now, we have computed for this first order system the outputs corresponding to unit ramp, unit step, and unit impulse inputs. Now, in the reference input column, the step input and the impulse input are derivatives of the ramp and step inputs respectively. Interestingly, we observe in the output column a similar relationship. We can generalize this observation in the following way. In a linear time invariant system, if you differentiate your input, the output will be the derivative of the output corresponding to the original input. Similarly, if you integrate your input, the output will be the integral of the output corresponding to the original input, plus an integration constant. This integration constant can be found using zero output initial condition. Moreover, this property is not limited only to differentiation and integration, but holds for any linear operation applied on the input side. In fact, any linear operation applied to the input of a linear time invariant system affects its output by the same linear operation. Now we shall proceed to second order systems. Studying second order systems is important not only for their own sake, but also for the clues they will provide us in studying higher order systems. Let us base our discussion on the operation of a DC motor. If you apply a current to the windings of a DC motor, it will create a torque which we show by capital T, and this torque will rotate the load, which is assumed to be composed of rotational inertia and rotational friction. The moment of inertia and the friction coefficient are denoted by capital J and capital B respectively. The output of this system is the angular position theta. Modeling such a DC motor is quite simple. We assume that the torque is proportional to the current. In other words, the torque is equal to K sub T times the current I. Here, K sub T is known as the torque constant or the motor constant. To derive the transfer function, let us first write the torque balance equation. The torque generated by the motor will be equal to the sum of the torque to accelerate the load and the torque to overcome the friction. Taking the Laplace transform of both sides of this equation under zero initial conditions, we can find the ratio of theta of s to I of s, in other words, the transfer function from the input current to the output angular position. Now we can model the closed loop system as in this block diagram. the angular position of the load is measured and compared to a reference input, and then the error is fed to the motor via an amplifier. We can obtain the closed-loop transfer function as the feed-forward transfer function divided by 1 plus the open-loop transfer function. And then simplifying it, we obtain k over js squared plus bs plus k. Of course, here k is the product of the amplifier gain k sub a and the motor constant k sub t. Let us divide the numerator and the denominator by j so that we have a monic denominator. Then we can use the quadratic formula to factorize this denominator. Examining the discriminant of this quadratic polynomial, we find out that we will have complex conjugate poles if b squared minus 4jk is negative, and we'll have real poles if b squared minus 4jk is greater than 0. And for the equality to 0, we will have double poles. At this point, let us redefine the parameters in this second-order transfer function. In doing so, not only we will have a simpler notation, but also our parameters will be directly related to the behavior of the output. Let us denote k over j as omega n squared and b over j as 2 zeta omega n. We will further call zeta omega n as sigma. As we shall see in a few minutes, omega n is in fact the undamped natural frequency of the system, zeta is the damping ratio, and sigma will be called attenuation. So in its new form, our transfer function is given as omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. In this new form, the sign of the discriminant of the denominator polynomial will depend on zeta. So we will analyze the unit step response of the second order system for 3 different cases of zeta. The first one is where zeta is between 0 and 1. In this case, the poles are complex conjugate and the system is said to be underdamped. We can factorize the denominator polynomial by considering that the real part of the poles are minus zeta omega n and by calling the imaginary part as omega sub d. Since the sum of squares of the real and imaginary parts of the poles has to be equal to omega n squared, we can express omega d in terms of omega n and zeta as omega n times the square root of 1 minus zeta squared. Now, to find the Laplace transform of the unit step function, we multiply the transfer function with 1 over s. To take the inverse Laplace transform, let us first apply a partial fraction expansion with 2 fractions, one having the denominator s and the other one with the denominator of the second order polynomial of our transfer function. To shape the second term as the Laplace transform of exponentially multiplied sine and cosine functions, we can first separate a complete square in the denominator and then arrange the multiplicative constants, which brings C of s to a form that is now easily inverse transformable by using the Laplace transform formulas for sine and cosine functions multiplied by exponentials. So C of d is now composed of a unit step, a cosine multiplied by an exponential function, and a sine multiplied by an exponential function. Note that the unit step function, which we applied as the input to the system, is also a component of the output. In other words, the forced response appearing at the output. The rest of the response is oscillatory, and the frequency of oscillation is omega sub d. That's why omega sub d is called the damped frequency. Since the sine and cosine functions are of the same frequency, we can collect them in a single sinusoidal function. To do this, let us parenthesis out the factor 1 over square root of 1 minus zeta square and denote zeta as cosine beta. Therefore, sine beta will be square root of 1 minus zeta square, and tangent beta will be the ratio of these two expressions. We can now substitute cosine beta and sine beta into the expression for C of t, and then we can use the sine formula for sum of two angles to obtain C of t in a more compact form. And finally, beta is most conveniently expressed by using the formula for tangent beta. That means the output is composed of a unit step function and a sinusoidal function that is decaying in an exponential envelope. This figure shows a typical behavior of C of t, and this one shows how the error converges to zero. Note that as the damping ratio zeta tends to zero, the oscillatory part of the response will be equal to cosine omega n t, and it will not be decaying. So we will have sustained oscillations with frequency omega sub n, that is the undamped natural frequency of the system. Secondly, we shall consider the case where zeta is equal to 1, which corresponds to a critically damped system. In this case, the denominator of our second order transfer function is a complete square. So if we multiply it by the Laplace transform of the input, namely 1 over s, we can do a partial fraction expansion with three fractions having the denominator s plus omega n, and the square of s plus omega n. That means in this case, the time domain expression for the output will be composed of a unit step, an exponential function, and a time multiplied exponential function, which will result in a behavior as in this figure. So we do not have oscillations at the output anymore. Nevertheless, the output seems to approach the reference value quite fastly. Lastly, here is the case for zeta is greater than 1, which corresponds to an overdamped system. Once more, let us recall our second order transfer function, and the output will be this transfer function multiplied by 1 over s. In this case, the roots of the denominator polynomial of the transfer function are real and distinct. We can find them by factorizing the polynomial, and we will refer them as minus s1 and minus s2. In this case, the coefficients of the partial fraction expansion can be easily found by the residue theorem. And C of t will be composed of a unit step function and two decaying exponential functions, which can be expressed either in this form or this form. To consider an extreme case, let us assume that zeta is much larger than 1. In this case, S1 will be much larger than S2. In fact, S2 is approximately 0, whereas S1 will be approaching to 2 times zeta times omega n. So in the above expression for C of t, S1 minus S2 multiplied by S2 can be approximated as S1 times S2, which in turn will be equal to omega n squared. Since S1 is very large, the exponential term e to the minus S1t will die out very fastly, and under these assumptions, the output will be reduced to 1 minus e to the minus S2t. In other words, as the damping ratio gets higher and higher, the system will behave more and more like a first-order system, which you can observe in this figure showing a typical behavior of C of t. Here you can see the variation of unit step response of a second-order system with respect to the damping ratio. The output C of t is plotted for zeta equals 2, 1, 0.7, 0.5, 0.3, 0.1, and 0. Note that for zeta equals 2, the response is an overdamped one. For zeta equals 1, it is critically damped. And for zeta less than 1, the response gets more and more oscillatory with decreasing zeta. Finally, for zeta equals 0, 1 has sustained oscillations at the output. From this discussion, we understand that the output of a second-order system is shaped by the parameters zeta and omega n. On the other hand, in synthesizing such second-order transfer functions, we need to also understand the relation between these parameters and the time domain specifications that are given to describe the behavior of the output. Therefore, we shall continue by defining some typical transient response specifications which are used to define a desired behavior of the output for a step input. One of these specifications for such a typical oscillatory response is, for example, the delay time. That is the time required for the response to reach half of the final value. Another one is the rise time, the time required for the response to reach the final value. And whenever the response is non-oscillatory, you can define it as the time to reach 90% of the final value. As another specification, you can give the peak time, that is, the time required for the response to reach the first peak of the overshoot. Of course, peak time is applicable only if the output exhibits oscillations. Also, you can give the maximum overshoot, the maximum value of the response measured from the final value. Maximum overshoot can be specified as an absolute value or as a percentage with respect to the final value. Lastly, you can also use settling time. Settling time is the time required to reach and stay within a range about the final value. Typically, this range is either 2% or 5%. In practice, you would need 2 or more of these specifications to describe completely what you expect from your output. Next, we will explain how these specifications can be related to the parameters defining a second-order transfer function. Let us first start with the rise time. At the rise time, the unit step response must be equal to 1. From the expression of C of t, it follows that the terms in the brackets should be equal to 0. And so we can write the tangent for omega sub d times tr as minus in the square root 1 minus zeta square over zeta. Multiplying the numerator and the denominator of this ratio by omega sub n, this expression can be simplified to minus omega d divided by sigma. And then we can solve the rise time t sub r in terms of omega sub d and sigma. To understand the relationship between the pole locations and the rise time, first recall our second order transfer function and the expressions relating omega n, omega d, zeta, and sigma to each other. Let these be the locations of our complex conjugate poles on the complex plane. Note that zeta omega n, in other words sigma, is the negative real part of the pole, and omega sub d, namely the damped frequency, is the imaginary part. Also, since the sum of the squares of the real and imaginary parts of a pole is equal to omega n squared, the natural frequency gives the distance of a pole to the origin. Revisiting the formula we derived for T sub r, we note that the ratio omega sub d to sigma is the tangent of the angle between the pole and the negative real axis. In other words, minus omega d by sigma will be the tangent of pi minus beta. So by comparing this formula with the one above it, we can write the rise time as pi minus beta divided by omega d. So the rise time is inversely proportional to the damped frequency. That means increasing omega d will decrease the rise time. In other words, the larger the frequency of the oscillations, the faster will the response climb up to the final value. Also note that cosine beta can be given as zeta omega n divided by omega n. In other words, it is equal to zeta. So keeping the damped frequency fixed and decreasing zeta would mean moving the pole location parallel to the real axis towards left so as to decrease beta, and changing the pole in this way will decrease the rise time. Next, we consider the peak time. The peak time is when the first maximum of the response occurs. In other words, whenever the derivative of c of t is equal to 0. Differentiating c of t, we'll see that the cosine terms can be cancelled and we can collect the sine terms together. Now the exponential term and the terms in the brackets are non-zero. So at the peak time, sine of omega dt must be equal to 0. Or omega d times tp must be a multiple of pi. Since we are looking for the first peak, Tp must be equal to pi over omega d. Like the rise time, the peak time too is inversely proportional to omega d. That means the larger the oscillation frequency, the faster will be the first peak reached. To find the maximum overshoot, we can subtract the final value, that is 1, from the value of the output at the peak time. So we substitute pi over omega d for t in the expression of c of t and subtract 1. We can cancel omega d terms, and noting that sine pi is equal to 0 and cosine pi is equal to 1, we can obtain the expression for maximum overshoot. You can express it also as a percentage. Note that the maximum overshoot depends only on zeta. That is, the larger the damping ratio, the smaller will be the maximum overshoot. Lastly, we shall consider the settling time. We should first note the discontinuity of settling time with respect to the error percentage. To see this, let us examine this part of the graph in a bit more detail. For a given error percentage, we might, for example, have a settling time that is given as this. Here you can see that for a very small increase in the error percentage, the settling time jumps to a considerably smaller value because of the oscillatory nature of the response. Therefore, we will base the calculation of the settling time to the envelope of the response rather than the exact value of it. For example, the 2% settling time will be obtained by equating the exponential envelope of the oscillations to 0.02. Similarly, you can equate the same function to 0.05 to obtain the 5% settling time. To simplify things further, we are going to approximate the square root terms with 1. And further approximating e to the minus 4 by 0.02, the settling time based on 2% criterion can be obtained as 4 over zeta omega n. Similarly, since e to the minus 3 is very close to 0.05, the 5% settling time will be obtained as 3 over zeta omega n. Note that the settling time is inversely proportional to zeta times omega n, that is the attenuation sigma, and therefore it is directly determined by the real part of the pose of the system. As an application of what we have seen about the second-order systems up to now, let us consider again the position control of a DC motor. Remember that we had an amplifier and a DC motor in the feed-forward path, and the loop was closed by a unity feedback. Also, we obtained the closed-loop transfer function in terms of the parameters K, J, and B. Further, we defined the square root of K over J as the undamped natural frequency of the system, namely omega sub n, and we have defined the damping ratio zeta such that B over J equals 2 zeta omega n. This means that zeta can be defined as B divided by 2 times square root of jk. Now, besides feeding back the angular position, we are going to also apply a velocity feedback. To obtain the angular velocity of the load, you don't need to differentiate the position. You can measure it directly by a device called tachometer. Note that now we have 2 feedback loops. Therefore, the closed-loop transfer function can be written now as the feed-forward transfer function divided by 1 plus the sum of 2 open-loop transfer functions. Simplifying the terms in the numerator and the denominator, we can arrange the transfer function into a form with a monic denominator. We see that the natural frequency of the system is still square root of K over J. Nevertheless, the 2 zeta omega n term has been changed. In fact, instead of B, zeta is now proportional to B plus K times K sub H, and both K and K sub H are positive. In other words, zeta has now become larger. That means the velocity feedback has the effect of increasing the damping of the system without changing the natural frequency. Now, let us assume that the moment of inertia is given as 1 kilogram times meter square, And the friction coefficient is also given as 1 Newton meter divided by radians per second. The desired performance is specified in terms of the maximum overshoot and the peak time for the unit step response. We are going to determine the gains K and K sub h to meet these specifications. We are going to also find the rise time and settling time corresponding to these gain values. Since the maximum overshoot is specified as 20%, we can solve for the damping ratio as 0.456. On the other hand, since the peak time is 1 second, the damped frequency turns out to be equal to pi. Also, the natural frequency can be found as 3.53 radians per second. Since the natural frequency is equal to the square root of k over j, or simply the square root of k since j is equal to 1, the value of the gain k can be obtained as 12.5. And finally, using all these values for zeta, omega n, b, k, and j, one can solve for the gain k sub h as 0.178 seconds. To find the rise time, let us first find beta as the inverse tangent of omega d divided by sigma, which yields 1.1 radians, and then we can obtain the rise time as pi minus beta divided by omega sub d, that is 0.65 seconds. To find the settling time, we can use the formula 4 divided by zeta omega n for the 2% criterion, which yields 2.48 seconds. Similarly, the 5% criterion settling time is 1.86 seconds. You can use all these values in a MATLAB Simulink model to simulate this control system. The graph here shows the output C of t obtained from this simulation. Note that the output rises up to 1.2 around t equals 1 second, which is as demanded by the transient specifications. And this brings us to the conclusion of this video. Do not forget to go over the examples and exercises in your textbook to check that you can distinguish between transient and steady-state response, that you can derive transient responses of first-order systems to basic types of input, that you understood the dependence of the shape of unit step response on the transfer function parameters of a second-order system, that you understood practical meanings of basic transient response specifications, and that you understood the relationships between the transient response specifications and the transfer function parameters of a second-order system.